All right, so now I want to handle a couple of issues. One is just going to make these algorithms better, and one is going to make them converge faster. I guess that breakdown might have made sense in my head, but as I was saying it, it doesn't make sense. So what I mean is the following: um, we're gonna do something to make it converge faster. But one of the issues that we have is that in order to call this function, we need to know an approximation for the size of the Krylov space. This is kind of like calling SOR, but having to know how many iterations you want it to do ahead of time. Now that doesn't really make a whole lot of sense. The method should just go until it produces a solution, or until it's been going at it so long without getting a solution that it just stops and says, I can't give you a solution, I'm not converging, right? So that's how the method really should work. And so that's what we're going to do here. So I'm going to make a new method, a new function here, FOM cycle 2, and it's going to fix that problem. And so what it's going to do, the difference here is that FOM cycle 2 is going to take a couple of new parameters. It's going to take a parameter called check every. Whoops. We give it a default value of 100. So the check every means that after every 100, it's going to build a subspace up to size 100. It's going to check the residual. If it's what we want, it's going to return. If not, it's going to create a next subspace up to size 200, check the residual, or solve the system, check the residuals. If it's what we want, it's going to go up to 300 and 400 and so on and so forth. An important thing is that it's not restarting. It's not going up to 100, taking that value for the solution, and then restarting again from a size 0 subspace up to 100 and so on and so forth. So this is not a restart method. This is a we're building up, and if we're done, good, we return. If not, we keep building up. Okay, so we're still going to have, if you run 100, if we run 500 iterations, we're still going to have a subspace of size 500. So check every is going to be 100, and then we're going to say the maximum number of chunks. That is, how many of these things do we want to do is going to be equal to 10. These are default values. The user will be able to pass in other values. Okay, so again, this says we'll do after 100, we'll check. After 200, we'll check. 300, check. 400, check. All the way up to 1,000. That's going to be the maximum size of the subspace we do is 1,000. And then by then, we're either just going to return with what we have, or we're going to, we've returned before with a good solution. Now, what we have to do, we have to have a stopping condition. And our stopping condition needs to be based on a relative tolerance like we've seen before. So it's going to be, we want our residual to be less than or equal to relative tolerance. So our relative residual wants to be less than or equal to tolerance, or our residual is less than or equal to relative tolerance times the norm of p. So we're going to have that. And I'm going to give it a default value of 10 to the minus 5. You can do it however you want to. Now, a lot of things are going to stay the same. The biggest thing that we're going to have is down here. So breakdown is equal to false. I'm going to call it chunk counter. We're going to start this at equal to 0. J is equal to 0. So now our M here is going to be equal to check every times max chunks. So check every, that's the size of the chunks, times max chunks. Okay. You know what? I'm going to, instead of check every, that's what I had before. I'm going to call it chunk size. Okay, and I will let you change this doc string on your own. Okay, check every, and then we're going to have chunk size to get all of the chunks in here. Okay, my wife would not like me calling that. That's one of those words that she doesn't like. All right, so now this is just while we have not maxed out the number of iterations we're going to do, basically. Okay, all of this is exactly the same, no change here. But what we are going to do is the following. Let me give myself some space to work. We're going to say if chunk counter is equal to the chunk size. If I happen to write check every, it's just because it's a typo, because I'm reading what I have prepared. It says check every, so if I write check every, just because I haven't translated, it'll be a typo. We'll find it, and you guys will probably notice it 20 minutes before I do. Okay, so now what I need to do is I need to set up, I need to solve the system of equations, but notice I haven't finished yet. Like I haven't finished, I haven't gotten, but before up here, when I was solving the system, I was done, okay? But I'm not done here. So two things could happen. If I happen to break down right here, then J is equal to L. If I haven't happened to break down there, J is still equal to L. So what I need to do is I need to set up my vector. So I'm going to say BE1 is going to be equal to NP dot zeros. Okay. What is the size that it needs to be? Well, I'm going to be multiplying it by H. So it needs to be the size of H, which is J. Then BE1 of 0 is going to be equal to R0 norm. Okay, and now we're going to do Y is equal to SP dot lin alg dot solve H bar up to J. I like to put those together. Okay, this is all right, I believe. BE1, unless I've made a typo. Okay, this is just exactly what we've done before, but in an earlier stage. So solution is going to be equal to x naught plus V, boom, 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 okay, times Y. So Vy is our delta, remember? Okay, and now we're going to look at our relative tolerance. So R is going to be equal to NP dot, what if I, sorry, I have a weird thing in what I have from before, and I'm a little bit confused by it. Oh, yes. So this is going to be our residual. So it's going to be NP. The naive thing is to have NP dot lin alg, dot norm, something like B minus A times solution. Okay, that's a naive thing. But remember, there is this formula. This wouldn't be horrible, but it's going to involve matrix vector products followed by computing the norm. Remember, there's this formula that says that the norm of the residual is equal to the bottom right entry of the H matrix, that is the entry that was just computed, times the last entry of the Y vector. So instead of doing this, we're going to do R is equal to NP, and those are exact equality. It's exactly equal to that, not just bounded by that or approximately equal to that or something like that. So we're going to have H bar J minus 1 times the last entry of Y minus 1, like that. And now what we're going to do is we're going to say if R is less than what? Okay, so this is the absolute residual. So we're going to say if R is less than the relative tolerance times the B norm, then we're going to do something. So that means we are within our tolerance and we want to return. I'm actually going to change this in just a little bit. So return the tolerance and R divided by B norm. And we're also going to return J. That is roughly the number of iterations. Yeah, okay. Roughly I mean, I know it's the number of iterations, but I forget exactly why I did that. I don't think I actually used it. I don't think I used it a lot. Oh, no, I did use it. Never mind. Okay. In the testing. Okay, now the only thing is that this right here, what we really need to have is it needs to be, we also have the absolute tolerance. So we need to make sure it's also, if it's less than absolute tolerance, we need to return it. So what we're gonna do up here is we're gonna say target is gonna be equal to max tolerance, which is the absolute tolerance, and then rtol times b norm. Okay, otherwise we could have something that is essentially what could happen is if we have something that is so small that it's never going to converge, and we're just going to do all of the iterations, which is not exactly what we want to have happen. Okay, so we're going to return that. If we don't return that, what we need to do is we need to increase the chunk counter. So let's see, not increase the chunk counter. We need to set it equal to 0. Okay, so that's going to be there, and then in the outer loop, we always need to increase the chunk counter. Sorry, just plus equals 1, right? Okay, and then now, okay, there's two ways that this loop can exit. Breakdown, we return, or j is equal to m, in which case we're going to compute everything within the loop, so we don't need to compute this solution again, because we've already computed it up here. Okay, because how do we get into this size? How do we get into how do we get into this loop right here if chunk counter is equal to the chunk size, and that's going to happen on the very last iteration through this loop if we don't make it, if we don't exit before then. So this is what we want here. Then we're going to do j here. Okay, that looks fine. Okay, now let me come down here. So this is FOM. So now we're going to do FOM cycle 2. And we need to give it a chunk size, which I'm going to say the chunk size is equal to 50. And I'm going to say max chunks is equal to 10. Actually 100. This means we're going to do at most sort of 500 different, we'll build, 5,000, a subspace of size 5,000, which I think is going to be way too big. And I'm going to say relative tolerance is equal to 1e minus 6 for now. No, let me do 1e minus 8 for now. Or what was I getting here? 7. Okay, let me do 7. So there we have that. That should work out. Oh, the number of iterations. I'm going to do in here. FOM2 time. Where do I, for SOR, where did I put the number of iterations? At the, okay, and. Okay. So in, cross your fingers. Okay, oh, you know what? I wanted to do this 32 first. Hold on. All right. Oh, check size. I did not mean check size. I meant this to be chunk size. Okay. Yep, you guys probably saw that typo. How many other typos are there? Yeah. Okay. Oh, yes. Okay. because what I need to do with V up here, these ims need to be changed to chunk size times max chunks. That's not a typo, that was just a mistake. Okay. Okay. So notice, you know, for FOM, if we don't know ahead of time how many iterations we need to do, we just have to guess something big and hope it covers it. And we have, you know, we've gotten to 0.9, you know, 10 to the minus 0.9 there, or sorry, 10 to the minus 9, which is good. But notice we've just gone to 400 iterations here. Okay. And of course, it's taken much less time than SOR, even though I'm even using the fast SOR there. And then GM res here takes a little bit longer. Okay, so let's... and then also SOR takes 60,000. I mean, this is really amazing. I mean, 6301 divided by 400 is 158 times as many iterations. But if you look at the difference between between runtime 0.735 divided by 0.0830, I think. Okay, it's only it has 158 times the number of iterations, but you know only takes 8 times as long to run, which is I don't know. I think this just shows. This just definitely shows where the pinch point is, or the thing that takes a long time for these projection methods to run, and it's going to be in the building of the subspaces. So if there's a way that we can make the building of the subspaces faster, it's going to help things out. So it's not really the solving of the linear systems that's taking a long time. Okay. So now what I want to do now is I want to make a GMRes2. So I have this. So I'm going to come down here, copy and paste down here. I'm going to call this GMRes2. And again, the only thing that's going to be different, the only thing that's really going to be different is going to be, well, there's going to be a couple of things. This is going to be different, and also our check for the tolerance is going to be different as well. Okay, so let me... all right, so this is going to be least squares, LST square, and then this exactly the thing that we had before. I actually have not found that I found that not including this, let me say it this way. I have not found that not including this actually changes anything. So we're going to have this, and now, okay. Yeah, okay, no, this is going to be the same thing that we check as well. Okay. Let me just make sure I have this all correct with the indices. I do it ahead of time so that I do not have to guess. Okay, so now do the same thing for GMRes2. Okay, so let's run this. Okay, 400 iterations. Okay, so here's the printout here. Okay, so the GMRes, you know, if we're just guessing at the number of iterations, it's really hard to actually use because you just have to do it for more iterations than maybe you need to do it. So this is not something that I want to have in my life right now. So I'm going to get rid of these, and I'm going to get rid of these. I'm going to run this again. By the way, if you try NumPy takes much longer. If you just try numpy.lineage.solve, that takes much longer. If you try scipy.sparsesolve, it's going to take orders of magnitude shorter. Okay, so with the matrices that we have now, sparsesolve is still the one to use. Now, I do not understand this. If you use, my experiments have been that if you use scipy's GMRes function, it's also going to take a very long time, or it's like orders of magnitude more. Less than NumPy, way less than NumPy, but also way slower than what we're doing. I have some reasons for that to make that make sense to me, but it's still an interesting fact to me. And let me just bump this up to 64 to see how GMRes runs. So I'm gonna post this, and you can test these things with the other code that I put up there for the 3-dimensional code, and you should start to see differences. If you use sparsesolve, you should start to see some differences between time differences between GMRes and the sparse solver. Okay. So I'm actually a little bit surprised that this has not converged yet, because it seemed to converge. So for something like this, I probably should have changed the chunk size to 100 and made this 50. So it's checking. So it's not checking as often. All right. Yeah. Okay. So it maxed out its iterations. So that's interesting. It took a little bit less than a minute. And so we should expect that GMRes is going to have something very similar. It's probably going to max out its iterations as well. But notice that it's now having to solve a 5,000 by 5,000 system, which is not, and it's a 5,000 by 5,000 dense system. So it's a getting into non-trivial sizes of systems that it's solving. You know. So the next thing that I'm going to show you is a way that we can speed up this convergence. But it's not running. It's not finishing its run yet, so we're going to have to wait a second. Wow, this is taking way longer than I expected. Okay, I guess you can just wait and speed up the YouTube video. The reason it's taking longer than I expected is because when I ran it with this size, when I ran it with this size, I had done the thing that speeds up the convergence, and so it didn't take forever. Okay, you know what? I'm just gonna kill it. Okay. Let me put it back to 32 just so I can make sure everything is running properly. Okay. So here's what we can do. Remember, we talked a little bit about preconditioning the system. In fact, we were able to look at all three of the methods that we learned before, Jacobi, Gauss-Seidel, and SOR, as a preconditioned version of Richardson iteration. So what does that mean? So we have a system that we care about solving. I'm going to type it right here. AX is equal to B. And the idea is we come up with a matrix P, and P is going to have the property that P is approximately equal to A. So what does that mean? Well, we want it so that P inverse times A is approximately equal to the identity matrix. That's what we want. Okay, and the idea, I mean, obviously A inverse fits this description literally and the best, but the idea is that we want P inverse to either just be straight up easy to compute, or at least systems like Px equals B are much easier to solve. So what we're going to do then is we're going to mathematically, what we do is we multiply both sides of our equation by P inverse like this. And the idea is that if A has a bad condition number and P inverse has a good condition number, then overall this will have a good condition number, and so it will converge better. So one of the easiest things that we can do here, especially for the matrices that we're going to be looking at, is to take P equal to D, that is the diagonal part of A. And computing the inverse of the diagonal of the matrix is very easy. It's just, we just divide by the diagonal. And so what we're going to do up here, instead of running this with A and B, we're going to run it with the following. We're going to run it with 1.0 divided by A, its diagonal. Now, what I just typed, and we're going to multiply by A. Now, what I just typed in, this is going to be a dense matrix, okay? And we want it to be a sparse matrix. So we're going to have to tell it it's a sparse matrix, so SPS dot diags. So it's going to create a sparse diagonal matrix where that is on the diagonal. Okay, and then for B, we're going to do something similar. It's going to be B divided by A dot like this. Okay, and now let me just make sure this is going to be correct. Okay, we're going to replace all of our well, not all of it, just for these two. All right. So notice for FOM2, before we did the precondition, it was running 400 iterations. At least I think that's what it was. And then after the precondition, it just runs 150. Okay, so now we see GMRes. It was running 400 iterations before the precondition. Let's see how many iterations it runs after the precondition. Okay, 150 as well. And so now you can see it's taking much less time. It's taking much fewer iterations. And remember, the number of iterations is really, the cost of each iteration is huge. So if you can decrease the number of iterations, that's great. So let me try 64 again and see if look. I mean, before, remember, I had 64 and it was like taking forever to converge. And now it just basically converged instantaneously. Now, this is one of the easiest preconditionings that we can do. The code that I'm going to post has better preconditionings, and so you'll be able to see how to do that. But the preconditionings in general, we're not going to be able to compute this matrix here. So if we have some, in the code, we're going to want, like, for example, in the precondition system, like for the Arnoldi step, we're going to want to do something like this in principle, or not. Remember, we have W in the Arnoldi step. So this is the matrix. This is like the left-hand side. So we're applying our algorithms to this matrix. In principle, that's what we're doing. We're applying our algorithms to this matrix. Okay, so in the Arnoldi step, it's not going to be A times R naught. It's going to be P inverse times A times R naught. Okay, if P is the diagonal matrix, this is all fine. We can just put it put it here, and it'll work. We can just run the code literally with P inverse times A. But in general, that's not going to be possible. And so instead, anytime we do some sort of multiplication like this, what we're going to do is solve this system for W. We know what A is. We know how to do A times R naught. We know what P is. So we're going to solve this system for W. So that is the way that we multiply by the inverse, is to solve this system right here. So I will post that code so you can look at it. But then, because in a couple of weeks, not next week, but the week after, in week 9, I'm going to talk a whole lot about preconditioning. Okay, but again, just notice how much faster this runs with this very simple preconditioner. And one thing that I haven't tried, I don't know what's going to happen if I precondition. I do not know what's going to happen if I precondition SOR. I haven't thought through like the logic of that. Hold on. I didn't get everything, did I? Okay, let's see what that does. Wow. Okay. So, well, why did SOR? Oh, because, okay, so let me bump this up to 9. Or bump it down to 9, I should have said. Yeah, okay, so we can see that it takes many fewer iterations. I think it was like 36,000 before. Anyways, I hadn't even thought about that. Anyways, precondition the precondition. This is like in Dominion, the throne room, a throne room. All right. I forget exactly why I ran this again. I think just, because I wanted to see how many iterations the unpreconditioned SOR had. I don't remember it taking this long. Anyways, I'm going to post... Okay, there we go. Oh, it maxed out the iterations. But it got a pretty good error there. Okay. I bet if I did this with fewer iterations... Sorry, now you're just sort of getting a stream of consciousness. Anyways, so I'm going to post... I made 3 videos for the lab. I'm going to post the 3 lab videos. One is for Arnaldi method. One is to show how to code FOM and GMRes. And one is this current video that tells you kind of how to do it, make this stuff a little bit better. And I'm going to post 2 Jupyter files. One is the one that I've just worked on, and one is basically one that I was working on before that has it has the more sophisticated preconditioning. But we're going to talk about, you don't have to do that stuff for the homework. We're going to talk about preconditioning in week 9. But that is going to be it for this video.